We're going to zip on to problem 5. Another old AP free response problem. Loving these, huh? You loving these AP problems? You will. They're good. They make you think. Okay, it's good for you. All right, things that make us smarter, we like that. We like being challenged. Okay, here I've got a small block on top of a big, long slab. Okay, what's going to happen is the slab is sitting still, and this block starts off moving already at 4 meters per second to the right. So it's going to start sliding along here. The coefficient of kinetic friction between the block and the slab is 0.2, but there is no friction between the slab and this horizontal surface here. You say, huh. Now, if this is sliding along, it's going to rub on this slab. And that friction is going to shove that slab to the right. There's no friction with the ground, so the slab is going to start sliding to the right while this is sliding to the right. Furthermore, this started at rest, so the slab will be accelerating right. And then this block on top of it is accelerating too, getting slower. You're like, oh my gosh, they're like both accelerating at different accelerations. Wow, that messes with your head. How's it eventually going to end up? Assuming this doesn't slide off the end of the slab, eventually this slab's getting slower, this is getting faster, because as they're sliding past each other, they're rubbing and pushing on each other. But eventually, is it possible this guy would slow down to be going the same speed as the slab, and then they're not rubbing, they're not going to shove it anymore, they'll just move together at that final speed at the end? That's interesting. That's really interesting. Okay, maybe, though, this is going so fast that maybe it will slide off the end. That's a good question. If they gave us some values, we could figure out what would happen. And maybe like how far, where it ends up. Wow, this could be a really cool problem. Okay, anyway, they tell us the mass is the initial speed of this guy, and they say coefficient of friction, and there we go. On the dots below, can you draw and label vectors to represent the forces acting on each as the block slides on the slab? And so you say, okay. All right. I don't know, side by side if this fits in frame. So I'm going to have to do it this way. All right. So, you know, they gave me dots. I'm going to draw it on boxes because, you know, I like boxes. So here is the block, and here is the slab. All right. All right. And so I'm going to do my forces. Starting with the block. Range forces, there's gravity. Okay. So there's going to be mass of the block times g. All right. Contact forces. It's only touched by one thing, the slab. Are they pressed together? Yes, they are. So there'll be a normal force on the block by the slab. Are they trying to slide past each other? Yes, it is definitely going to be sliding along at the start, going at 4 meters per second when the slab starts at rest. Yep, slab at rest. And so this will be trying to slide right on the slab, so there'll be a friction force to the left. This is friction on the block by the slab. Alrighty, now the slab. Range force will be gravitational force, mass of the slab, right, times g. Okay. And then, yes, and then contact forces, you say two things are touching the slab, the floor, horizontal surface is what they call it, and the block. Are the slab and the block pressed together? Yes, they are. Gravity presses it into the slab, and so the slab is going to be pushed. There's a normal force on the slab by the block, NSB. This is an action-reaction pair with NBS, of course. And then you say, are those trying to slide past each other? Yes. The block is sliding to the right, and so friction on the block is to the left. Well, if the block is sliding right on the slab, it's like the slab is sliding left. You know what I mean? And so the friction force on the slab will go the other way. Friction on the slab by the block. Now, the other thing touching the slab is the horizontal surface. What am I going to call that? H, horizontal surface, fine, we'll call it H. It's pressed into H, so H will press back up with a normal force. This is a normal force on the slab by the horizontal surface. And then are those sliding past each other? Yeah, the slab is going to start sliding to the right, but they told you it's frictionless, so I don't put a friction on. Okay, I've now talked about everything touching these guys, and there's no ropes or strings, so there's no tensions. This is it. These are our force diagrams. All right, if I was doing this on the dots, right, then what you end up with here, look, it's the block. Look, it's the slab. All right, and when you do this, you would end up with Okay, and when you first look at this, you don't know for sure what these arrows represent. You know what I mean? And with this guy, I would have and then I suppose this. There's some people that tack the arrows onto each other's lengths, but I think most of us would do it like this. You know, and the point is that when I first glance at it, it's not obvious what these arrows all represent. When I look at these, I see an arrow along a surface. I'm pretty sure it's a friction. I see an arrow from the middle going down. I'm pretty sure that's gravitational. I see arrows from the surface shoving in. I'm pretty sure those are normals. Even without the labels, I'm pretty dang sure what these arrows represent. On this, I got no idea. It could be tensions, could be great. Anyway, you get it. I prefer this to the dots, but dots is what they did. I would label them with this. You need to have them labeled to get the points. Okay, now at some moment later, before the block reaches the right end, both the slab and the block attain identical final speeds. Makes sense. As this is sliding right, it's going to get slower, and then this is going to be speeding up because of this friction force rubbing on it. That slab is going to speed up to the right until they're both going the same speed. Then they're not trying to slide on each other anymore. They're moving together. And there'll be the friction force will go away, and we'll be going constant. Both horizontal forces will go away. That's just the friction, right? Action, reaction. And so we'll just be moving at constant speed. They would like us to find that final speed. Okay, there are various ways of doing this problem. There's a really slick way of solving it using momentum, but I'm not going to do that one for you today. That is the fastest way of solving it, for sure, by the way. If you can do a conservation of momentum on this system, treating them both as one big system, do you see how that would turn out? It would be so quick to do. In fact, I'm going to do it that way real quick, and then we'll do the force way, okay? The force and kinematics way, and you'll see how much faster the momentum way was. Here, let's do it. We're gonna cheat, and we're going to use momentum. You recall that the central formula for momentum is that the impulse is the change in momentum. The impulse is the force times the duration is equal to the change in the momentum of the system. But what I'm going to do is I'm going to cheat. I'm going to make both of these one big system. If these were one big system, these two friction forces are equal and opposite. They would drop out. Forces between parts of my system drop out. I would just have the vertical forces, right? So, and those are all going to balance out because we're not accelerating up or down. Well, then you're like, oh my gosh, there's no horizontal forces. You know what that means? Overall, this system has a constant momentum. There is no outside impulse in the x-axis. With momentum, we can analyze each axis separately. In the horizontal axis, we realize there is no net force, and so there is no change in momentum. That means the initial momentum equals the final momentum. So that means the change, so it means my initial equals my final. Initially, I've got this mass, half a kilogram. This would be m times v plus mv equals mv plus mv. Mass 1 initial, mass 2 initial, mass 1 final, mass 2 final, right? Except we recognize that at the start, m2, the slab, is sitting still. So velocity is 0, so that drops. m1, we know what that mass is. We know the initial velocity, right? At the end, they're moving together at the same final velocity, so that v final is the same. I can factor it out. Do you see what I'm saying? So what I have here is just the mass of the slab, the block, I mean, which is 0.5, times the initial velocity, which was 4 meters per second, plus 0, equals, at the end, I'm going to have mass of block plus mass of slab, 0.5 plus 3, I'm fine, 0.5 plus 3 times the final velocity. So you see, look at that, 0.5 times 4. You're like, I can see I'm going to be able to solve right away for v final, and I'm going to get 0.5 times 4, that's 2, equals 3.5 v final. 2 over 3.5 is v final. You're like, 2 over 3.5, what's that going to be? Isn't that like, that's not good math. That's like 4/7. You're like, okay, 4/7 is my v final. Meters per second. Okay, I'm not going to do a metric conversion. A decimal conversion, but you get it, right? I did go all the way up the bottom of the paper when I did that. Oh, I'm so sorry. But you recognize what we're doing here, right? Verbally, it made sense, I hope. when we talk through it, we're going to do mv plus mv is mv plus mv because the initial equals the final momentum because there's no outside horizontal force to change the horizontal momentum. So the change in horizontal momentum is 0, so it's constant. I just put in my values. And I recognize that I know everything except VF. I can solve for VF. Okay, that is the slickest, fastest way of solving that problem. But if we are trying to do forces and kinematics, then we have a tougher row to hoe here. So here we go. Using kinematics and forces. Woo. Okay, hey, for the block. A, V naught, V, delta X, and T. You're going to say, well, I don't know what the acceleration is of the block. I know its initial velocity is 4 meters per second, and its final velocity is that V final we're trying to find. Delta X, don't know that. Time, don't know that. And you're like, oh, you gotta be kidding me. If I talk about the slab, you're going to say acceleration, don't know. Initial velocity, 0. Final velocity, that's that V final. Delta X, don't know, right? Time, don't know, right? You're like, oh my gosh, what is going on here, right? Okay. Now we do know that it's the same time for both, okay, to reach that final velocity. The T's are going to be the same. The delta X's aren't quite going to be the same though, okay, because this block will slide some on the slab, right? Meanwhile, the whole slab moves. The slab moves some distance, but the block is going to move that same distance plus the length along the slab that it went. Do you know, does that make sense to you? I hope so. So the point is this delta X is not the same as that one. It's related by as that extra distance it slides along the slab. Okay, for the block. Alrighty. Whew. But there is a relationship there. So maybe I can do something with that at some point. The T's being the same means I'm going to be able to like sub and solve through the two equations perhaps. If I find the A for one, I can find the A for the other. You know what I mean? Or whatever. So there's some hope there. But I clearly need some more information. I have to have 3 variables to solve for a fourth. I need more information. Now, since the T's are the same, that's good. If I can get 1A, I think I'll be in good shape. So I'm going to find acceleration from F equals ma. So let's go to the block and do sigma F in the X is mass times acceleration in the X. And that's just going to be a minus that friction on the block by the slab is the mass of the block times that acceleration of the block. Friction is going to be mu n. This is kinetic friction. We're sliding along. So it's a kinetic mu. This is NBS, MBAB. You say, hey, here's that acceleration I'm going to need for plugging into here, right? And so you say, well, gosh, to get that, I got to rearrange this. You say, I don't know what n is. I'm going to get n from the vertical axis, knowing that these jerk, 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 jerk. Would you be upset if I just jumped right ahead and said n is MBG? Thanks. I appreciate it. So I'm going to have, and the mu they did give us, right? They told us that the coefficient of friction was 0.2. So that's good. NBS is going to be MBG. Is MB acceleration B. You say, oh my gosh, the mass of the block is going to drop. That's awesome, right? So this is minus 0.2, 9.8. That is my acceleration of the block. That is going to be a fifth of 9.8. I should be able to do that. That's going to be 0.196. Is that right? 1.96. Negative 1.96 meters per second squared is the acceleration of the block. Okay, now I have that value. So now I have 1, 2, V, and then T we know is the same for both. So I'm going to use that variable because it's going to show up in the other equation, the equation for the slab too. So if I run through, should I write the kinematics equation down? Sure. A, V naught, V, and T is the equation that doesn't have delta X. That would be V is AT plus V naught. So that final velocity is that acceleration, that negative 1.96 times T, plus initial velocity, which was 4 meters per second for that guy, right? Right. Okay, that gives me an equation that's got 2 unknowns, V final and T. Let's go to the slab, all right? Now we go to the slab side. Whew. Wish I had color coded that another color. Oh well. Nope, not gonna oh well it. I'm gonna do it. Okay, I'm gonna make the slab orange, okay? So doing the slab, some of the forces in the x is mass times acceleration in the x. In the x, I have just this force, friction, going in the direction to the right. I'm sorry, of course I'm calling x and y and calling it the right positive. So this is going to be friction on the slab by the block is mass of the slab times that acceleration of the slab, right? But I don't know the acceleration of the slab. I'm going to try to figure it out here. This is going to be a mu normal on the slab by the block equals mass of the slab times the acceleration of the slab. Hey, how big is this normal force? Well, this one's a little more complicated, isn't it? Oh. No, it's not, because NSB and NBS are an action-reaction pair. So this guy and this guy are the same size. We found that, look at that, we found that that normal force was just MBG, right? So I can put MBG there. Mass of the slab, acceleration of the slab. Okay, so my acceleration of the slab is going to be mu mb over msg. All right, I know these values, 0.2. Mass of the block is 0.5. Mass of the slab is 3. And of course, G is 9.8. And if I punch in my calculator, I'm going to get that the acceleration of the slab, let's see here, 0.2 times 5 times 9.8 divided by 3 is 3.26666. So that's 3.27 meters per second squared. Notice that the block has an acceleration in the negative direction. It's slowing down. And the slab has an acceleration in the right. It's speeding up until they have the same final velocity. Okay, so now I know this value. I can put it in up here, right? Right? So we can do a kinematics equation there. And again, we've got A, V naught, V. We're trying to find that final V. And then the T, and the T is the same T from here, and the V final T. So I've got to have, so I'm going to use the same formula that doesn't have delta X. So for the block, for the slab now, I'm going to do V is AT plus V naught. So V final is the acceleration of the slab. That's 3.27 times T plus V naught. V naught for the slab was 0. So look, I've got an equation here, right? Got these two equations, right? And they've got the same V final and the same T. You're like, now I have it. And you say, I can rearrange this for T, substitute it in here, and get my V final. Ta-da! So if you do that, you're going to say, hey, T is V final over 3.27. This, put it in there. So I'm going to have that final velocity, negative 1.96 times V final over 3.27 plus 4. And you're like, all right, let's see. I got to move this term to the other side and then factor out the VF and then move that back. Okay, and this is where I'm running out of paper. So I'm going to slide this up. I'm going to say we're going to end up with V. I move this term over, it's going to become positive 1.96. And then I'm going to factor out the V final. So it'll be V final times 1 plus 1.96 over 3.27. Right? See what I'm saying? Okay. See what I did? Move that over and factor out the V final. Okay, now I'm going to move this underneath. So my V final is going to equal 4 over the quantity 1 plus 1.96 divided by that 3.27. Conveniently, that 3.27, the exact value is still in my calculator here, so that'll be good. Here we go. Punch it in the calculator. 4 divided by the quantity 1 plus the quantity 1.96 divided by answer, closed quantity, 2.5. The V final is 2.5 meters per second. And you say, Son of a gun, that is not what I got there. What did I do wrong? By the way, notice how much faster it was to get this momentum answer? Whew. Okay, did I do some math wrong in my head? 0.5 going at 4. Half of 4 is 2. Okay, and that one, the slab was sitting still. Afterwards, it's going to be both of them going at V final. That's 0.5 plus 3 kilograms, right? Yeah, so that's 3.5. 2 over 3.5. Yeah. Yeah. Yes. This is definitely right. Okay, this 4/7 is definitely, there's no question about it. Which means I made some bonehead mistake somewhere in my calculation here, in this long calculation. All right, now I have to find my mistake. Okay, block starts at, yes, 4 meters per second, that's fine. Final speed is V final. Yes. Yes. Mu n. N is mg. Mass is going to drop out for the block. So 0.2 times 9.8 is going to be that, right? Just I'm not. Yes, 1.96. Yes. Okay. That makes sense. Okay. AT plus or not, right? Yeah, that all checks out. Okay, that I'm happy with what I did in green. Let's go to the slab. That friction is what's driving it to the right. Is the mass slab times right? That normal force is just mg, right? Oh, 0.2 is my mu, right? I'm not crazy here. Yep. Times the mass of the block divided by the mass of the slab, right? Times G. Yeah. This acceleration, right? This value makes no, this value makes no sense. I screwed up this calculation here because if these forces are equal and opposite, right? Then this is the smaller mass. Equal force, it should have a bigger acceleration. This is a bigger mass. It should have a smaller acceleration with the same force. This acceleration is bigger than that. That can't be right. My mistake must be here. So let's try that. Okay, I bet it's like 0.327. I bet it's like a factor of 10, like I did my decimal point wrong. I bet is what it is. I bet. 0.2 times 0.5 times 9.8 divided by 3. 0.326. That's it. That's what I did. This decimal point belongs there. So it belongs there. The decimal point belongs there. There. This is not going to be 2.5. All right. Sorry to waste that time. I apologize. Okay, so running through this is going to be 4 divided by the quantity 1 plus quantity 1.96 divided by, now this value came out to be 0.32. It was like 6 repeating, you know what I mean? So we can do this for a while. Anyway, okay, I messed that up. Look at what I did there. What is that? 1 point, what? Oh, got it. 4 divided by the quantity 1 plus 0.32, right? Close that parenthesis, close that parenthesis. Bam, 0.54142. That is the same thing we got here. Okay, that's it. That is in fact the 4/7 meters per second. Okay, which is approximately 0.571 meters per second for V final. There we go. Whew. Okay, you're like, holy cow, man, sakes alive. We got the same answer out, but boy, it was a lot more work. You're much more likely to make a dumb mistake like I did, sorry. But you say, yeah, it was a lot more work to go through with kinematics and F equals ma. Look what we had to do. Holy cow, to find that final velocity. Whereas with conservation of momentum, pretty dang quick. So One of the key things in AP Physics and in the AP exam is that they'll give you situations and you have access to all of the techniques for the course. And you have to decide what approach you want to use to the problem. And you can see it makes a big difference sometimes whether you use one approach or the other approach. Man, I would much rather solve this with momentum than with F equals MA. Whew. Okay, so having that, now we're going to go to the next part of the problem, because that was just that part. They now want us to calculate the distance the slab traveled once it reaches V final. And you're like, well, now though, see, now it's all going to pay off, right? That hard work we did, because this is just a kinematics problem now. It's a constant force, that kinetic friction is constant, right? And so it's a constant force acting, so it's a constant acceleration, so we could use all this kinematic stuff. And so for the slab, you'll recall, we are now on part C, right? Part B was finding, this was part A, part B was this calculation here. Okay, part C, we want to find for the slab, we're trying to find how far it went, right? The horizontal displacement, distance the slab has traveled the moment it reaches VF. And so for the slab, hey, look, we've got A, V naught, V, delta x, and t. And you say, look, we now know all these values. We found the acceleration. That was that 0.326666666, right? We found the initial velocity was 0 for the slab. The final velocity, we just found the final v was 4/7 meters per second. We can find that. That's just a quick, that's quick now. That's quick. That's quick. I want the kinematics equation that doesn't have t. That'll be v squared is v naught squared plus 2a times the displacement. Rearranging this mess for displacement, it's going to be v squared minus v naught squared over 2a. That's going to be that 4/7 meters per second squared minus 0 over 2 times that 0.326 bar over the 6, right? Punch that in my calculator. Woohoo! That's your 4 divided by 7, quantity squared. Sorry, 4/7 squared minus 0 divided by the quantity 2 times 0.3266666. Okay, 0.4997. We're just going to round that off and say that is 0.5 meters. Okay, that is how far the slab is going to slide before it gets to that final speed. Okay, and lastly, they want to know, calculate the work done by friction on the slab from the beginning of its motion until it reaches V final. And you're going to say, work done by friction. Now, we can try calculating this a couple different ways. One way you say, this is now an energy calculation, which I know we haven't talked about yet, but you'll recall that work is, you were taught last year that it's the force dotted with the displacement. Okay, that's how I calculate the work. So if I want the work done by friction, that'll be that friction force times the distance, the force that it goes. The friction on the slab is to the right, and the motion slab is to the right. So that dot product, remember there's a cosine theta hiding there. That's going to be a cosine of 0 degrees, which is just 1. So it's just the friction force times delta x. And you say, hey, can we solve for how big that friction force is? And you say, sure, friction is mu times the normal. And we figured out before from the force diagram, we said, hey, that normal force here is the same as this normal force here is the same as mg for the block. And the mu we know is 0.2, so this is going to be mu times mass of the block times g times the distance, right? Okay, 0.2, mass of the block is 0.5, that's 9.8, and this is where we hit a snag, all right? The snag is, yeah, the block slid along this distance. So the slab slid along some distance that we just solved for here. but the block rubbing on it actually slid farther, didn't it? Because it slid along the slab some distance while the slab was moving. You know what I mean? So this friction force was applied through a longer distance than just how far the slab moved. Does that make sense to you? You know, so I believe that this will not get, if I plug this delta x in, I don't think I would get the right answer. I think I technically would have to add on the distance that that block slid to it, and that would give me the correct answer. So what I'm going to do, yeah, okay, I'm pretty sure that's going to be the case. Here's the thing. Here's what I think is going to happen. I think that yes, I say. If I apply that force through the distance the block slides, actually that's going to give me the correct value for the work done to increase the kinetic energy of the block. But that extra work that's done, because it actually moves along the block while it's shoving, is going to be the energy that went into thermal energy in that rubbing. I believe that is going to be my answer. Yeah. So if I want the total work done by the friction force, then I have to worry about that extra distance that the block slid along the slab. If I just want the energy that's transferred as kinetic energy to the slab, then I don't have to worry about the extra distance that the block slid along the top of the slab. So that's I think my answer, and I'm sticking to it. So what are they asking for? The work done by friction on the slab. Well, do I count the thermal energy that was transferred? Well, the problem is the thermal energy, some of it stayed in the block too, so I don't think they want that. I think they just want the energy transferred to the slab. So I believe I'm just going to use that 0.5 meters, okay? And that's going to be fine. So I'm rounding that to 0.5. Do you care? I didn't think so. So if I do that, that's going to be 0.2 times 0.5 times 9.8 times, and remember that this value that I, no, it's all good, times 0.5. And you say when I do that, I'm going to get 0.49 newtons. I mean Newton meters, or if you like, 0.49 joules of energy, okay, is the work done on the slab. All right, let's check this answer. Hey, if I'm thinking this is just the energy that goes into making the slab move, then this is the kinetic energy I gave the slab. And kinetic energy is 1/2 mv squared. This had no kinetic energy at the start. It was sitting still. So the work is the change in the energy. It's this kinetic I gave it. 1/2, what's the mass of the slab again? 3, yeah. The final velocity was 4/7 meters per second, right? Yeah. Am I thinking about the previous problem? I'm thinking about the previous problem. Holy cow. What was the final velocity we came up with here? It was right there. Sorry. Oh, it was 4/7 meters per second. Yes, that's right. No, that's fine. That's fine. Okay, so let's just do the math on that. If I do, this may not work. I may be wrong. 0.5 times 3 times the quantity 4 divided by 7 squared. This isn't going to give me that. But look at that, 0.49. Look at that. Okay, I feel good about that. Okay, shoo.